Okay, so welcome back, everybody, to the last talk of this afternoon session. So I'm Nicolas Burke, and I will be the moderator for this talk. And it is my great pleasure and honor to welcome Semyon Dyatlov from Massachusetts Institute of Technology. And he will speak about the fractal uncertainty principle and quantum chaos. Semyon, it's you to speak.
Thank you very much for having me here. So, well, this is going to be a somewhat specialized talk since it's PD and dynamics section. And I will tell you about quantum chaos and various applications of a new kind of theorem called the fractal uncertainty principle. So here is a broad overview. So I'll present a few results in quantum chaos. Some of them are results on compact manifolds, so lower bounds on massive eigenfunctions, results in semiclassical measures, which is a kind of classical object to study in quantum chaos. Observability for Schrödinger equations, which is another classical question to consider. And then I'll also talk about applications to open systems, so when the manifold is non-compact and the energy can escape. So the proofs of all of those results are roughly based on the same circle of ideas, though the details are of course different. One is we use the classical quantum correspondence to its limit. So there is a general understanding in the study of, say, wave and Schrödinger equations that at high frequencies, solutions to those equations should propagate along straight lines or geodesics or along the trajectories of some classical system. Now, this correspondence is, at some scale, it is valid. For example, geometric optics and why light travels in straight lines is an example of that. But at some point, it breaks down for longer times, at lower frequencies and whatnot. And so we take this correspondence to its limit. We use it as much as we can until it really breaks down. And at the point where it breaks down, we inject this tool that has nothing to do with classical quantum correspondence. It's instead a tool from harmonic analysis. And that lets us get results that you couldn't get by using classical quantum correspondence alone. So this new tool, I call it the fractal uncertainty principle. I'll give you a precise statement later, but a rough statement is that no function can be localized in both position and frequency near a fractal set. Okay. So one of the limitations of these results is that this fractal uncertainty principle in general is only known in dimension 1. And as a result of that, most of the results I'll present here will be in the setting of surfaces, so manifolds of dimension 2. In the last slide, I'll mention some hopes for removing this or proving higher dimensional results in the future. All right, well, here's a special thanks to my mentors and collaborators. Especially I mention Jean Bourgain, who was already mentioned profoundly in today's plenary talk by Larry Guth, who unfortunately is no longer with us. All right, so let me go on to state the first result. So there will be a bunch of results. And so first result I'll present is the one that's simplest to state, and that's about eigenfunctions on a negatively curved surface. So I'm going to take a compact negatively curved surface, a Riemannian manifold of negative Gauss curvature. And the reason why we look at the negatively curved surface in study of chaotic systems is because the geodesic flow on the surface is a standard model of classical chaos. It has very unstable behavior. So if you perturb a geodesic generically, infinitesimally, just a little bit, then as time goes to infinity, it will diverge. This perturbation will diverge exponentially fast from the original geodesic. So you have very high sensitivity to initial data. So it has strongly chaotic behavior, this geodesic flow. And then a typical object to study in quantum chaos would be the quantum counterpart of this, which is eigenfunctions of the Laplacian. So if you think of geodesic flow as telling you how classical particles behave on your Riemannian manifold, eigenfunctions of the Laplacian give you pure quantum states of a free quantum particle on this manifold. Now, of course, we don't live on a negatively curved surface. The dimension is wrong and some other things are wrong too. And it's good. It's good to not live in a highly chaotic environment all the time. But there are lots of, this is mathematical congress and not a physical one. So we certainly can study it as a mathematical question, but also there are a lot of physically relevant systems that do exhibit chaotic behavior. I'll mention one experimental connection at the end of the talk. Okay, so here's the result. So here are my eigenfunctions of the Laplacian. I'll make them L2 normalized. I'll call the eigenvalue lambda squared. And I'm going to fix a non-empty open set in my surface. And then the theorem is the following, that you have a lower bound on the L2 norm, so on the mass of this eigenfunction on the set by some constant. And this constant, well, of course, it has to depend on the manifold and on the open set, but it does not depend on the eigenvalue. So in particular, what will matter is that it does not go to 0 in the high energy limit when the eigenvalue goes to infinity. Right? The way you can interpret it is this L2 mass, well, squared, is the probability of finding your classical, your quantum particle in this set, omega. So it tells you that this probability is bounded away from 0, in particular in the high energy limit. So here are the references for this. So it was first done in the case of constant curvature for hyperbolic surfaces, which is a very important special case that comes up in a lot of places. In joint work with Jin, using joint work with Zal and the Fractal uncertainty principle coming from joint work with Bourgain. And the variable curvature, it was done more recently in joint work with Jin and Non and Masher. Okay. All right. So I should say that if you freeze the eigenvalue here, if you know a bit of elliptic PDE theory, you will see that this estimate would be well known because it's a unique continuation principle. So if you fix lambda here, it's just an elliptic partial differential equation. And for those, you know that solutions cannot vanish identically on a set, and there's a quantitative version of that. But for general manifolds, the constant in the unique continuation principle would decay exponentially in lambda as lambda goes to infinity. I'll show you one example of that on the next slide. So the novel result here is that this constant is fixed and it doesn't depend on lambda, so it doesn't degenerate in the high frequency limit. So it's really a high frequency result on behavior of pure quantum states if you want to interpret it physically. Okay, well, here's an illustration. So there's two pictures. So one is, okay, it's a boundary value problem. It's a disk. So I put Dirichlet boundary conditions there. And this is a plot of a typical eigenfunction on the disk. And it has a lot of interesting features. You can compute it explicitly using Bessel functions. But a generic eigenfunction on the disk, eigenfunction of the Laplacian, would have this white space in the middle. It's not literally white, but it's, again, exponentially small in the square root of the eigenvalue. And so the theorem would certainly fail for the disk. I can take my body, my omega being in the center. Here's the plot on a hyperbolic surface. So that one is harder to get. And this is courtesy of Alex Strohmeyer. So, a hyperbolic surface, one way to think about it is you can cut it. And then you can glue it together from pairs of pens, or you can glue it together from a hyperbolic polygon. And so that's what it is here. You have a Poincaré disk model of the hyperbolic space. You have this polygon, and you glue those ends, and then you get your surface. So that's a typical way to plot something numerical on a hyperbolic surface. And here's a picture of a typical eigenfunction. I actually saw maybe a few thousand of those pictures, and they all look the same from afar. And you can see in Alex's color coding white, so 0 is orange. So you're plotting here absolute value square of the eigenfunction, I think. And you see there is no macroscopic orange space. It has a lot of zeros, of course, the eigenfunction. It has to. But if I fix a macroscopic set, then the mass in this set will be bounded from below. Okay. So it's kind of funny interplay of microscopic versus macroscopic. So for instance, if you're sitting on the first row, then you might see this has a lot of interesting features. And from an eigenfunction to an eigenfunction, they will change all, ever so slightly. If you're sitting in the back, it looks like just a blur. And one of the big conjectures in quantum chaos is that on macroscopic scale, these eigenfunctions equidistribute. So they all look like they're just distributed everywhere equally. So here's an application to PD. So maybe you don't like eigenfunctions. Maybe you believe, like some people, that eigenfunctions are this result of a human desire of associating discrete objects to continuous phenomena. So here is a result that doesn't feature eigenfunctions. Instead, it talks about a time-dependent problem for the Schrödinger equation. So we again have a compact negatively curved surface, again fixed in an empty open set. And now we look at a solution to a linear Schrödinger equation here. So that depends, this is a time-dependent one. It describes evolution of a quantum particle on the surface. And what we show is that you have an observability estimate, namely the total mass of the solution, so let's say the mass of the initial data which is conserved, is bounded in terms of the L2 mass of the solution in just this open set omega in x, but for positive range of times. So here I can try to give you some pictorial or physical explanation for why maybe the results should be true, or kind of what it means from, again, a quote-unquote physical point of view. But let me first say that the only other setting in which such a result is known is the case of flat tori. And here are the references for that case. So it goes back to early 90s. So if we look at this room, for example, right, it's more or less a 3 torus, right? Now, if you think about, let's say I draw some set. So I have my set omega, let's say my kind of general aura here. And this is where I can observe things. That's where my sensors are in some hypothetical experiment. That's where I measure what happens. Do we have classical trajectories of particles, just bouncing off the walls that never enter this set? We do, right? For example, I can imagine, again, an idealized particle or a ball just bouncing up and down like this, and I never see it. So from a classical point of view, I will never observe this particle from this set. So what does make, why does quantum result like that work? Well, because a particle cannot be exactly localized on a given trajectory. There is the classical uncertainty principle that tells you that a particle has to blur out at least a little bit in its localization. It cannot have precisely determinable position and velocity. So it has to wobble, it has to spread out a little bit. The wave function has to spread out. And so, for example, if it spreads out a little bit in velocity, then what will happen is that it's not going to be exactly vertical. Instead, it's going to do this, right? And then it'll bounce, and then it'll bounce like that. Maybe it'll bounce a little bit forward also. And then if you think about, say, the geodesic flow on the torus, you know that if you have an irrational direction in which you shoot, this trajectory is going to be dense. So somehow part of the particle has to live on those trajectories that have to be observable, that have to intersect this observation set. So eventually, some part of this particle mass will bounce on some irrational trajectory and will cross my observability set, and at which point I will measure it. And so I'll be able to estimate somehow the total mass by what happened in this observable set. Now, this is what happens for the torus. What happens for hyperbolic surfaces is that the dynamics is much more chaotic. So each of those trajectories would be even more chaotic. You would have a very fast divergence from the initial point. But it's harder to control quantum classical correspondence there. And that's where this fractal version of the uncertainty principle comes into the proof. Okay, another application that I'm not going to really explain in detail here is that you can get exponential energy decay for solutions to the damped wave equation. So, if you don't like quantum things, here is a kind of an application to a wave equation problem. All right. So now it's going to get a bit specialized for the next 2 slides, because I have to explain a little bit the context of the problem and a little bit of the history of quantum chaos, where this kind of statements arise. And that means that I have to introduce a little bit of terminology. So a stronger version of this localization result can be obtained by using not only localization position, but also using localization frequency. So just like when I'm thinking about classical quantum correspondence, my particle doesn't just have position, it also has velocity. And then you think on the quantum side for the corresponding wave functions or eigenfunctions of the Laplacian, where's velocity there? And it turns out that velocity is encoded in the Fourier transform behavior of the particle. It's a non-trivial thing. I mean, it's been known in some ways since, I guess, late 19th century, but it's certainly a non-trivial thing to internalize and to absorb, and we won't be able to do it in the time here. But the way you think about it on a technical, mathematical level is you can start with an observable on the cotangent bundle of your manifold where cotangent vectors correspond to its velocities, and then you can quantize it to obtain an operator. So this goes back to quantum mechanics. And here's the formula, but I think I'm just going to skip a lot of details here, even the ones produced here. And so you start with a classical observable, a function of position and momentum. Momentum geometrically is a cotangent vector, and then you obtain an operator. And it depends on the parameter h. Physically, I guess it will be Planck constant. Here it turns out to be 1 over square root of the eigenvalue. Okay, so again, you'll just have to believe me about that part. And then what we can do is we can study the concentration of eigenfunctions of the Laplacian in the macroscopic limit. And so the way we could do it is we could fix a classical observable here. And then we can compute the following expression. We quantize it, get an operator, and then pair it with the eigenfunction. Again, this is a natural quantity that comes up in quantum mechanics. This is the average value of the classical observable A if the wave function is given by uj. So it's a standard quantity that you would study. And then you can take the limit. So my A is fixed, but the energy goes to infinity. So the eigenfunction changes, hj goes to 0. And you're hoping that in the limit you'll get an integral of A with respect to some measure for any observable A. And so if you have this situation, then you say that the sequence of eigenfunctions converges semiclassically to this measure mu on the cotangent bundle. So it's a way to extract a limit. You know, when you try to understand how things concentrate, say at high energy, you're forced to take a sequence of eigenfunctions and then try to pass to some kind of weak limit. Strong limit wouldn't exist because they oscillate faster and faster, but this kind of weak macroscopic limit might exist. And one way to see this limit is that if you push forward this measure back to the base, m, then you're just going to get the weak limit in the sense of probability measures, absolute value uj squared d vol g. Which, again, those measures, this is a probability density of finding your quantum particle at a specific point in a manifold, and so this push forward just gives you the probability distribution in the limit of your quantum particle, in the high energy limit. So you get those measures, and it turns out they always exist. There's some compactness theorem. And they turn out to have some wonderful properties that have been known for a while. They're probability measures. They're supported on the cosphere bundle, so they're supported on unit length vectors. And this one is compact now. And they are invariant under the geodesic flow. So there is this connection with classical dynamics here. Okay, going back to the results. So what can we say about those measures? So previously we had lower bounds on, on position concentration. And here we have a lower bound if you localize in both position and frequency. And the way we express it quickly is as follows, that if you take any semiclassical measure associated to a sequence of eigenfunctions, so you could have different sequences converging to different measures. But any such measure would have full support, which means that the measure of any in an empty open set is positive. So it's a stronger statement than Theorem 1. All right. And so in context of this, I can present you some previous results in quantum chaos. So the first one is quantum ergodicity, going back to work of, going back to the 70s. And that one says that on a manifold, if the geodesic flow is ergodic, then most eigenfunctions equidistribute, namely they converge in this weak sense to the Liouville measure. So that's what you see when you're sitting in the back and you look at this picture by Strohmeyer. That's what you see, that there's somehow their mass macroscopically seems to be just evenly distributed. And in fact, it's evenly distributed in position and in Fourier space. And that's what this result says. But it's only proved here for a density 1 sequence of eigenfunctions. So most eigenfunctions would equidistribute. So that prompts the question, well, can there be a sequence of eigenfunctions which does something else? And that's the topic of two conjectures. One by Colin de Verdière, which is the eigenfunctions cannot concentrate too much. So for example, what he conjectured is that you cannot have a sequence of eigenfunctions concentrating to a closed geodesic. Now here you need to make again some kind of chaotic assumptions. And in his conjecture he said negative curvature, which is a stronger assumption than ergodicity. right? And then there is the Rudnik-Sarnak quantum unique ergodicity conjecture that, in fact, the whole sequence of eigenfunctions equidistribute. So the only limiting measure is the Liouville measure. So you can see one is stronger than the other, right? The Liouville measure is basically just the volume measure on your S theorem. So it's equidistribution according to volume. So of course, the QE conjecture is stronger than the Coulomb-Dividier conjecture. Because here you just say, some very specific examples cannot come up. And here you say there's only one limiting measure. The Coulomb-Dividier conjecture was proved by Anand Tarman and Nonnenmacher some approaching 15 years ago. And the way they do it is, what they really proved is they proved the lower bound on the entropy of the limiting measure, which is a natural dynamical systems quantity associated to it. So they showed that the entropy is positive, and the entropy for delta measure on a closed geodesic, which is the most concentrated and invariant measure, can be 0. Quantum unique ergodicity is a big open question, but it is known in some settings. So Lindenstrauss proved it for arithmetic hyperbolic surfaces where you have a lot of extra symmetries called Hecke operators that you can utilize to get many more restrictions on how eigenfunctions can concentrate. All right, so now we're going to talk about harmonic analysis. And here is the main tool, as opposed to these previous results that I mentioned, that makes it possible for us to prove this new theorem. And that's the fractal uncertainty principle. So I will give you a precise statement. This is actually a statement without any caveats. But we first have to understand what a fractal set is. Everybody has their own understanding of what's a fractal set. So my definition of a fractal set for this purpose is going to be something called porosity. Namely, it's a quantitative version of saying a set is nowhere dense. What does it mean for a set to be nowhere dense? It means that every interval on the line, so here I'm talking about subsets of the real line. Okay? So every interval on the line has a subinterval that doesn't intersect the set. That's what being nowhere dense means. Well, porosity means that for any interval of kind of a restricted range of sizes, so this is this h, which is 1 over square root of the eigenvalue, so it's a small number, but there's a number going to 0. There exists a subinterval of relative size nu, which doesn't intersect the set. So here's a basic example. Here's a mid-third Cantor set drawn in black. Well, okay, the real mid-third Cantor set is measure 0 set. It's pretty hard to draw on a projector, but here's a kind of artist's rendition of a mid-third Cantor set. And you see, if I take a blue interval, I'll always be able to find 1 over 6 size, relative size subinterval, which doesn't intersect this black set. Okay? So that's an example of what it means to be a fractal set. It has a lot of holes at all scales and at different places. Okay, well, here is the result. So assume that you're given 2 porous sets up to some small scale. And this porosity constant is constant, this porosity parameter nu is constant, but the scale goes to 0. And then we get the following estimate. So for any function in L2, if its Fourier transform is supported in H inverse times this Y set, so you prescale it to high frequency, it turns out to be the correct scaling for this kind of problem, then only a small part of the L2 mass of this function is concentrated on the fractal set X. So you have 2 fractal sets, and you know that the Fourier transform of your function is supported on one fractal set, and then you restrict it to another fractal set, this function, in position, and you can only retain a very small amount of its L2 mass, namely you get this estimate where you have a positive power of h. So h is this large, h inverse is a large frequency parameter that goes to infinity, and so that's the, it's an asymptotic statement as h goes to 0. I know this is a bit confusing, but these constants beta and c, they only depend on the porosity constant. So what you should really think about is that your x and y should be h neighborhoods of fixed measure 0 fractal sets. Okay. So, yeah. Anyway, so it's a statement. It's interesting to contrast it a little bit with decoupling type theorems that were presented earlier today by Larry Guth. And there are certain similarities. One similarity is that in both cases we have something about the Fourier support, right? In one case, in case of decoupling, Fourier support was on the parabola. In the case of, in this case, the Fourier support is on a fractal set. And the conclusion is that the function shouldn't be too large on a small set. In case of decoupling, it's done by LP estimates. And in the case here, well, it's L2 estimate, but it's L2 only on this fractal set. So I'm only computing the L2 mass on this porous set. So that's some of, the other similarities that in both cases, groundbreaking contributions have been obtained by Jean Bourgain. So there are, of course, also a lot of differences. You see, this is not an LP type bound. Right? Decoupling is an LP type estimate. This one is an L2 type estimate, which you would think would be trivial, but it's L2 on this rather rough set. L2 estimates in general are trivial because of orthogonality that Professor Guth explained earlier today. But you do not get orthogonality once you restrict to X. Those waves are not going to be orthogonal, these individual pieces, once you restrict it to this fractal set. So that's one difference. And the other difference is that decoupling takes advantage of the curvature, right? You are localized on a parabola, and parabola has curvature. Here, instead of curvature, we have this kind of fractal structure. We have a lot of holes. Of course, you have to exploit it in a different way. So I'm not going to explain how this is proved, but it's proved using harmonic analysis. And the proof is inherently one-dimensional, which is, which is a problem. All right, so now I feel obligated to explain how this statement about fractal sets, and the very particular statement, right, this fractal uncertainty principle, as far as I know, has not been stated before this line of work was started. So, but that's still, it's a question of harmonic analysis and something fractal geometry. How do we use it to actually prove these statements about macroscopic limits of eigenfunctions? In particular, I want to show you where does the fractal set come from. All right, well, so this is going to be very, very sketchy. So remember that the first theorem was a lower bound in the mass of eigenfunctions. Imagine that you have an eigenfunction which is very small on some macroscopic set. Okay, I'm going to show you roughly why this is impossible. Well, so there's a lot of hand waving here and a lot of technology that goes into these two lines. But using a semiclassical quantization procedure that starts with functions in a cotangent bundle and maps it to operators, you can understand the notion of localization of U in the position frequency space. You can try to understand where it lives in both position and frequency space. Not completely possible because at some point you hit the limit of the standard uncertainty principle and you cannot understand it further. But up to a certain extent it's possible. And then using the field of microlocal analysis, which is a mathematical field behind the classical quantum correspondence, you can see that the way this eigenfunction is localized in position frequency space is invariant under the geodesic flow. Now, in general, I think it's a very powerful, it's an old idea, again, going back to geometric optics, though I think it's only maybe in the 60s and 70s that it coalesced in a kind of nice mathematical theory. It's a very powerful idea because you want to bring in the geodesic flow. You want to bring in the dynamics of the classical system. Or say if you have a particle, some quantum particle or light bouncing in this corridor, you want to bring, billiard ball reflection and just moving in a straight line. But the geodesic flow is not a flow on the manifold itself. Because in order to know where geodesic ends up, you need to know the initial position and also the initial velocity. So somehow, once you work in localization, this position velocity space, you can see it's also invariant under the geodesic flow. In a way that when you project onto the base, you just cannot see immediately. Again, up to a certain point. So again, that's the uncertainty principle still tells us that it's not possible to do precisely. There are certain limitations. We have to respect them when we work with these theories. But once you have these two rough ideas, you see that, okay, so I have my counterexample function. I know it's very small in this in this observation set omega. And then I know that it's also it lives on a collection of geodesics. You can think of it this way. So its localization, the position momentum space is invariant under the geodesic flow. What this means is that it should only live, in this sense, on geodesics which never cross my observed region. Right? You know, if you have a subset invariant under the flow and not intersecting this open set, then it has to be inside the set of trajectories of the geodesic flow, or the set of geodesics that never cross this set. Now that's where a confusing but essential part of the argument comes up. It's on our scale, it won't be possible to define localization to both of these sets at the same time, because we kind of take the classical quantum correspondence to its limit, but we will be able to define localization on sets of trajectories that don't cross the this observation set in the future or in the past. So you have these two localizations, and together you cannot make sense of them using the theory available to us, which will prove essential. But we know that individually each of these localization makes sense, and my eigenfunction has to be localized that way. Now this is the point at which we can forget it's an eigenfunction, because it turns out that these sets have porous structure. I'll show you a picture on the next slide. And the fractal uncertainty principle can be used that no function can actually, it can be used to show that no function can be localized in both of these sets at once. So you get kind of paradoxical localization that contradicts each other. So, all right, I think I should just move on from this slide. So here's an illustration of at least some of this. So I'll illustrate what happens in the classical side. So I want to show what these sets of trajectories that never intersect my observation set look like. Now, geodesic flow on a hyperbolic surface is harder to plot. For one thing, the phase space is three-dimensional, and this is just general harder to show on a picture. So here I'm just going to show you a 2D picture, and I'm going to use a different model just for the purposes of this picture, which is an Arnold cat map, which is just this. It's a linear map on a torus. Let's take matrix 2, 1, 1, 1. It's a classical example of a strongly chaotic map. Okay. And here I just define those sets. So I have my torus, it's a square. Numerically, torus is a square. And I have my set omega in white. Let's just take it a disk. And then I look at sets of trajectories of this cat map which don't cross it in forward or backward time. So for time 0, I just have 3 pictures that look the same. For time 1, I get this. You see, this new white blob is if I was not in this set initially, but when I apply my map, I guess for -1 time, I'm in this set. So you get this new blobs, right? You see, if your eigenfunction really didn't live on the white set at all, and it was invariant under the map, it couldn't live on these other white pieces either. So it have to be localized to both of these black sets on the left and on the right. And then I keep doing that. And if you've seen pictures of Arnold cat map, you can kind of imagine what happens. These ellipsoids, they become longer. But as they become longer, they also wind around, which is a typical feature of hyperbolic systems. And there's one more. There's one more. And MIT has great projectors, so I think we can see this picture as well. Yes. So it's good enough for resolution here. And you can see that those two sets, they have some fractal structure. They are porous in 2 different directions. Right, so this set will be porous in, I think, the unstable direction, and it will be smooth, so it's foliated basically by the stable direction. And when you reverse time, then you get the opposite picture. And so what fractal uncertainty principle will tell you is that no function, eigenfunction or not, can localize in both of these sets at once. Once you kind of squeeze it out to the limit of where you can define localization. Okay, and I said it's just an illustration, but actually there is recent work of Near Schwartz that used that model to prove an analog of these theorems for quantum cat maps, which is a very nice toy model in quantum chaos. All right, well, moving on, here is a little bit more results. And so all the results I presented so far were on compact manifolds. So you have this particle, and it has nowhere to go, or rather, it just has to keep bouncing around your manifold. And essentially, the result was saying that the quantum particle has to have a somewhat positive presence in any fixed non-empty open set if you let it evolve for sufficiently long time. Now here is a different kind of problem, which is non-compact manifolds. And so what I'm going to do is I'm going to look at a hyperbolic surface, so constant curvature -1, but I'm going to make it non-compact and I'm going to make it have these big open ends called funnels. That's another kind of typical object to study in hyperbolic geometry. There's not so many hyperbolic surfaces you could imagine. And so this kind of thing is one of them. This is a typical kind of infinite end, one of the two typical kinds. So if you have a hyperbolic surface, if you think about eigenfunctions on the compact surfaces in terms of the wave equation, I'm looking if we have, does anybody have a metallic object? No? Pen, maybe? Sorry, I should have really. Oh yes, I'll return this back. It's not going to be like one of those magician experiments, and then the keys will be in Michelle's pocket at the end of the show. But you see, if you have a compact surface, then you can think of eigenfunctions of Laplacian as having to do with the solutions to the wave equation. If you teach differential equations 1803 at MIT, do this Fourier method, how you can decompose everything in terms of eigenfunctions, right? And they never decay. But if you have an open system, like for example, this bottle is surrounded by a lot of air, and then let's say it goes all the way to infinity, if I hit it, the sound is not going to sound forever. Let's say I should drink more of it. Actually, it's a good experiment. Look. Did you hear this? Right, so you hear a pitch. That's the real part of what we'll call a resonance. But you also, it dies down at a specific rate. And that would be the imaginary part of what we'll call a resonance. Now I changed the domain. Now if you have a good music ear, I guess it got flatter, which means the frequency went down, but it also rang for longer, right? So you have this, and if each mode would have, okay, I should really, before I forget. Funnily enough, I just realized I have my own keys, but that will be less fun, I guess. You get complex numbers. You get numbers that correspond to the pitch, so to frequency of oscillation, and also to the exponential rate of decay of waves. Mathematically, you can see those numbers called resonances. So they are a replacement of eigenvalues as a discrete spectrum. You can see them as poles of the meromorphic continuation of a resolvent, and that's, again, there's a long tradition of study of these, featuring in particular Rafe Matzeo's thesis back in the 80s here at MIT. And if this talk is in two sections, right? So if you're in the PDE section, you might find this part more appealing because it has operators. If you're in dynamical systems, you might find this interpretation more appealing, which is a constant curvature phenomenon. But you can form a Selberg zeta function, which is an Euler product over lengths of primitive closed geodesics. If you form it correctly, the zeros of that are going to be the same resonances, which is a kind of, it's an amazing thing that's particular to constant curvature. So you get those resonances corresponding to kind of a generalization of spectrum of the Laplacian. And well, here is their interpretation in terms of solutions to the wave equation is that the real parts would be rate of oscillation. So what we hear is the pitch. The imaginary part will be rate of decay. So the inverse of the time that you hear it ring. So here are some plots of resonances. As you can see, they look somewhat complicated, and they certainly both have a real and an imaginary part. So these I just put for fun. They're due to Borthwick and Borthwick-Weiss. And you can see they look kind of complicated, and they have a lot of interesting features that you can study. But most of the time they actually look like that. So it's just a whole sea of resonances. And the result that we can show about those is something called a spectral gap, which is there is a certain number depending only on the surface, so that there are only finitely many resonances in the strip where this imaginary part is bounded, above by this number. So what this means in terms of the linear wave behavior is that you get exponential decay of linear waves. So somehow the pitch that you hear, or not the pitch, the going to higher frequency waves won't make it sound longer. This is the opposite of what you want to see in a musical instrument. When you make a hollow musical instrument, you want those resonances to be close to the real line. You want them to have small imaginary parts, because small imaginary parts means that it vibrates for longer. You can hear it for more. And so, unsurprisingly, most musical instruments look like a ball with an opening. Okay, maybe not quite, but topologically almost like that, right? The most basic musical instrument is you take a ball, you take a sphere, and you make an opening so that it could escape at least a little bit, and then you bang on it, and then there is a wave that's bouncing inside, and then it leaches out, but very slowly, and so you can hear it for longer. Now, the systems we consider, they are chaotic and in a way that's kind of opposite of that. And so we show that you actually have exponential energy decay of linear waves, at least at high frequency. And you can prove other things like Strichard's estimates, and it follows another long history of study of spectral gaps in this and other settings. But instead of dwelling on what these papers did, I'm going to show you a physically relevant example. So, as promised, which is scattering by several convex obstacles. So imagine you're looking at the wave equation in the exterior of several convex obstacles. It's the easiest open chaotic system you can think about. You know, if you're inside an obstacle, then you're not really chaotic. The waves can be trapped for a very long time. If you have one convex obstacle, then everything just bounces off and goes out, and that's not interesting. If you have two, you have exactly one trajectory that bounces back. Interesting, but maybe less interesting in 2022. And so when you start with at least three obstacles, what you get is you get this fractal set of trapped trajectories that just keep bouncing between the obstacles. If you solve the wave equation in the exterior, you feel that this set has to have some significance. That your waves, you should have some part of the waves that are trapped on this set. Now this set looks awfully complicated, and it is. But another way to plot it would be to reduce to the boundary and plot not only the positions but the velocities. And then when you look at trajectories trapped forward and backwards in time, you again see two sets which have this kind of dual structure. They have porous structure in one direction, smooth structure in another direction, which relates to what I showed for the compact case. And so using this, one can show, and so this was done by Vakosen, relying again on this fractal uncertainty principle, is that you actually get a spectral gap in this setting. So at least at high frequency, you get exponential decay, and the spectral gap is something that was previously observed experimentally in this six-author paper in PRL in 2013. So I went through the results, and now a little bit of outlook and what's bright or maybe not so bright future of this whole business. And this is one of the questions you want to know is what happens to in higher dimensions. So the results I mentioned, they apply to surfaces, dimension 2, which is not completely satisfactory. For example, we are in dimension 3. Sometimes, like those microwave experiments that I briefly mentioned in the previous slide, they were in dimension 2 effectively because they just have this big flat aluminum plate, and it's much easier to get kind of a flat aluminum plate than a whole big disk of aluminum, I suppose. So it's effectively two-dimensional. But still, you want to know what happens for general dimensions. And for that, you would need the fractal uncertainty principle for subsets of Rn where n is at least 2. Now that is difficult to prove because it's false. So we don't have anybody from logic here, do we? It's, Harvard could. But generally, false statements are very difficult to prove. We hope. So here's a counterexample, and it's a very silly one. Take two perpendicular lines. Take your x to be, say, a vertical line and y to be a horizontal line. If you take your function to be the delta function on x, then you take the Fourier transform, you're going to get the delta function on y. And so here's an example of a function which localizes on a set of smaller than full dimension in position and in Fourier space. As silly as it is a fundamentally difficult counterexample. And we don't know what to do with it, really. But there are some things that are known, and some give some hope. So there's a result of Hanschlag, which is you can show this result if fractal uncertainty principle, if one of the sets is a product of porous sets. So a line is not a product of porous sets. A line is a product of a point and the line. So that's Then there is a recent result joint with Jezekel, who is a postdoc here at MIT, which is in some cases, when the largest Lyapunov exponent, the largest expansion rate, is separated from all the others, it turns out that you can still use one-dimensional fractal uncertainty principle by very carefully choosing how long of a time you run the argument. Then there are some versions when x is a curve, and those actually take us back closer to the decoupling questions, how we can use curvature to prevent this counterexample from happening. And one that I think makes me particularly hopeful is this result by Cohen, who is a graduate student here, which is, it's an ultimate result for two-dimensional fractal uncertainty principle, but for a specific subclass called arithmetic Cantor sets, where things are certainly easier to work with, and that uses some algebraic geometry and number theory, as a matter of fact, to show that these two orthogonal lines, at least in this setting, is the only thing that can go wrong. All right, well, thank you for your attention.
Okay, thank you very much, Semyon, for this beautiful talk. It's really, once again, a pity that no questions can be asked through the system. So actually, Semyon told me that he will go to the Discord link. So there is a Discord link on the virtual ICM website where everybody can go and post questions. And Semyon, we will go and check the link and we'll answer the questions if you have questions. So do not hesitate. You can go to this link. You will find it on the website of the virtual ICM, and you can ask any question you want, and they will be answered. So sorry again for this impossibility to ask questions. And Semyon, thank you again for this beautiful talk.
Thank you for coming to my talk, and thanks to the IMU for the opportunity